These are some 5 SAT math hard practice questions that I will be attempting to solve. Let's see number 1. A bag contains tomatoes that are either green or red. The ratio of green tomatoes to red tomatoes in the bag is 4 to 3. When 5 green tomatoes and 5 red tomatoes are removed, the ratio becomes 3 to 2. How many red tomatoes were originally in the bag? That is indeed an interesting question. I guess I could do it like this. So we know that this is a ratio question. So one way we do this is we could set up a ratio, and I believe that we could do this through a system of equations. So right from we know what's called green tomatoes G and red tomatoes R. And the ratio of that is 4 to 3. Now when 5 green tomatoes and 5 red tomatoes are removed, the ratio becomes 3 to 2. So we know that the number of green or red tomatoes still does not change. So that's nice. Now the ratio is going to become 3 to 2. Now at this point, it just becomes some equations that you'll just solve out, and I guess we could solve this out. So let's just move this up here. So 4r is equal to 3g, while 2g minus 10 is equal to 3r minus 15. We could write it so that e1g is equal to 4r over 3. And then we could place this back in here. So 8 thirds r minus 10 is equal to 3r minus 15. And then you just solve this out with plus 3. So 8 over 3r plus 9 over 3r is equal to negative 5. And that's when I realized that I get a negative number. Oh, clearly because this is just it's just minus. I knew that. And then we could get to negative 1/3 r is equal to negative 5, and r is going to equal to 15 once we multiply this out by negative 3. So r is equal to 15, and our answer would be B. So let's look at the second question, I guess. Yes, the second question. So if each digit in an integer is greater than a digit to the left, the integer is said to be monotonic. For example, 12 is a monotonic integer since 2 is greater than 1. How many positive 2-digit monotonic integers are there? So we know that, first of all, they're going to be 2-digit. So now if each... Alright. So I'm going to take this workout. I'll just show it right here. So our logic now is that any greater after the first digit all the way to the left has to be greater than that. So we have to find a pattern. Starting from the tens, we know that 12 will be greater, 13 will be greater, 14 will be greater, and so on all the way until 19. How many numbers are that? 1, 2, 3, 4, 5, 6, 7, 8. That's going to be 8. Actually, I'll just write it all out for you. How many is that? 1, 2, 3, 4, 5, 6, 7, 8. That's 8. Let's try with 2. We have 20. What's the first digit that will become greater? It'll be 3. So now 24, 25, 26, 7, 28, 29. How many numbers are that? 1, 2, 3, 4, 5, 6, 7. So you see that as we keep going through each tens, when we start with from the 30s onward, it's going to be 6. From the 40s onward, it's going to be 5. So now we could just add all these up. So then for 50s, it'll be 4. 60s will be 3, 70s it will be 2, 80s it'll be 1, and 90s it will be. So now we just have to add all this up. So let's do this. That's 10. This is 10. This is 10. So you have 10s times 3, and then there's a 4 and a 1 remaining. So plus 5 is equal to 35. So the answer is going to be 35, and that's not an answer choice. Oh, my bad. We didn't take a 5, we took a 4. Plus 5 plus 1. 36. 36 is your answer. Let's go move on to 3. For a particular number a, the first term of the sequence above is equal to a, and each term thereafter is 7 greater than the previous term. What is the value of the 16th term in the sequence? So, okay. Because I already found it before, we're just going to start here. So, and each term there is, okay. So, what we can notice is that in this sequence, each next term in the sequence increases by some factor of a. Okay, this is a, 2a, 3a, 4a. And we also know from the question that each thereafter is 7 greater than the previous term. Okay. So that's interesting in my opinion. Each term thereafter, we have this. It's greater by 7. So we know all a's have to be equal to each other, and each term thereafter is 7 greater than the previous term. So that means that we could just choose any example here, and we could create a equation to model this. So we know that each term thereafter is 7 greater than the previous term. So that means 2a minus 1 is equal to 7 plus a. Because what we do know is that this term will be 7 greater than this, and this works out for everything. So we're just going to choose one example. So now what are we going to do? 2a minus 1, 7 plus a, we're going to figure out what a is. So a is equal to 2a is equal to 8 plus a, and then a is equal to 8. So we know that a is equal to 8. And now we could probably check back into here if this works. So let's look at this term over here. 8 times 2 is 16, minus 1 is 15. This term is 8 times 3 is 24, minus 2 is 22. So we see that this is still 7, so this works. So now we have to find the pattern between this and how we could get the value of the 16th term. So I could notice a pattern here. On the first term, there's an a. The second term, it's 2a. Third term is 3a. Fourth term is 4a. So you know the 16th term has to have 16a as part of its number, right? But you all see there's a minus 1, minus 2, minus 3. And now we can also know that for the first term, you're not subtracting anything. Second term, you're subtracting 1. Third, you're subtracting 2. 4, you're subtracting 3. So with 1, for the first term, you're subtracting, let's put this term and put what's happening. For the first term, you're getting minus 0. For the second term, you're getting minus 1. Third, minus 2. So we can see this pattern that whatever term it is, one less than that term, you're subtracting that quantity. So this will be 16 minus 15. We know a is equal to 8. We plug that back in. 8 times 16 is, I believe, 128 minus 15 is equal to 113. So our answer to question number 3 is 113. That's nice. So now question number 4. If p is a prime number, how many factors does p cubed have? So if questions like these, it's actually very easy. What we do with these questions is that you do these questions through example, because you'll notice that when they say this, they give the statement, you'll have to recognize that, oh, when the SAT writes these kinds of problems, this should work for any prime number. So you could always do these questions by example. So prime numbers are numbers that do not have any factors. So you just choose any prime number and you see how many factors does p cubed have. So let's choose the easiest prime number, 2. What is 2 cubed? 2 cubed is equal to 8. And now we just have to see how many factors it has. 1 is a factor, 2 is a factor, 4 is a factor, and 8 is a factor. The answer is 4. And we could probably check this while we're at it. We could try 3. 3 cubed is 27. Let's check how many factors it has. 1, 3, 9, 27. Easy as that. 1, 2, 3, 4 factors. Now our last question of the day. 5. How many integers between 10 and 500 begin and end in 3? So this is just really about recognizing patterns. So immediately you have to think about what digits between 10 and 50 will be in 3. It's kind of obvious, but what you do is you generalize this into a pattern, and then you think about this creatively, yes. So I have one number right here, 33. 33 is going to be one integer. And you'll notice that from 10 through 100, well, 10 through all the way to 300, you never, and you'll never, okay. Let's start. The only places where you start with a 3, you begin with a 3, is in your 30s and your 300s. Now, the only place where you'll have an end in 3 in the 30s is going to be 33. Meanwhile, for the 300s, you'll end in 3 in 303, 313, 323. You find that, oh, in 300s, I'm going to end in 3 whenever the ones digit and the hundreds digit is in 3. So now you just have to count this up. 303, and it's going to end in 393, 323, 333, 343, 353, 363, 373, 383, 393, 403. Doesn't work. Let's count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So your answer is 11. Thank you for listening. Bye-bye.